Am I audible? Hello. Am I audible? Can one of you can respond?
Yes, sir.
Okay, thank you. So good evening all. Welcome to the class today. So today we'll discuss some of the gist for the week 3 lectures and thereby some questions. Let me share my screen.
Yes, sir.
My screen is visible now. Can you confirm it? My screen is visible. Can someone confirm the screen is visible or not? Can someone confirm the screen is visible or not? Is the screen visible? Anyone can confirm it?
Yes, sir.
Okay, that's fine. So, we'll discuss in brief the lectures of week 3. So, so basically we started the discussion of spinel structure. So, spinels are basically of the form of A, B2, O4. So, here A and B is your metal, these two are metal, this is a non-metal. So, this O can be, can be X, okay, X can be oxygen or sulfur like that. So, this actually forms a cubic close packing, and there you have voids inside the structure there are voids. Okay, voids can be tetrahedral, voids can be octahedral in nature structurally. So out of this A and B, A is basically a divalent cation 2 plus, B is trivalent cation 3 plus. So how to decide this A plus will go to tetrahedral or octahedral, B3 plus it will go to tetrahedral or octahedral sites. Okay, depending on that, depending on site occupancy, we divide this spinel of two types. One is called normal and one is called inverse. Okay, normal spinels, what happen? This A2 plus will go to tetrahedral sites, B3 plus will go to octahedral sites. but invert spinel there will be a change. So B3 plus will come to the tetrahedral, and so as there are two B atoms or say ions, so half of them will come to the tetrahedral and another B3 plus plus A2 plus both will go to the octahedral sides. Okay, because B is double in number compared to A, and also depending on the ratio of tetrahedral versus octahedral voids inside structure. Okay, so how do you decide it? General thing is that you calculate. So this is a special term, this is called OSSE or octahedral side stabilization energy. This is nothing but you calculate the CFSE of octahedral sides, okay, of A2 plus B3 plus, and now you check that which one gives more stabilization. Okay, so let us understand through some example. It has been already discussed, but still for your clearing of doubts I will discuss it one more time. So general formula is Fe2O4. Let's say I am taking Fe3O4, so we can elaborate it as 1 Fe2, then 2 Fe3 and O4. This is your metal ions. Hmm? Now you have to check where it will go, tetrahedral or octahedral. Okay, so now what we will do, you check the CFSE of octahedral for Fe2 plus also and Fe3 plus. So Fe2 plus is D6 configuration, so it will be 4s 4s2 will go 4s0 3d6, and Fe3 plus will be 4s0 3d5. Now you check it. So how it will feel? So oxygen is generally weak field. Oxygen is generally weak field. Okay, so it will be high spin. That means it will be high spin complex. So high spin means, suppose you have these two, this is your EG and this is your T2G. So for D6 systems, how it will feel? It will follow the Hund's rule. 1 1 1 1 1. Now it will come back. It will pair up. So here you have your unpaired electrons. So what is the stabilization energy? CFSE. So this one you have how many numbers? 4 into minus, this is 0.4 plus you have 2 into 0.6. So minus 1.6 plus 1.2, you have minus zero point 0.4 delta O. Okay, this is your CFPC, and this is minus. Minus means it is stabilized. Stabilized. This is for iron 2. Now calculate for iron 3. Iron 3 will be, I'll do it with another color. So this is your levels. So only you have 5, you don't have another. So this time you will get CFC octahedral. So 3 into minus 0.4 plus 2 into 0.6. Then what is coming? Minus 1.2 plus 1.2. It is cancelling out. Then it will have 0. Okay, 0. So what you can see, in octahedral sites, the stability of iron 2 is much more than iron 3. So definitely it will go for this configuration, that is Fe3, half of Fe3 will come to the tetrahedral side, then Fe2, whatever Fe2 is available, it will go to the octahedral, and the rest remaining Fe3, it will also go to the octahedral, and you have the oxygen packing. Okay, this will be like that. So when this happens, we term it as inverse spinel. Okay, and while considering this octahedral site stabilization energy, general theory is that you compare the difference of CFSE between octahedral and CFSE tetrahedral. But we generally don't consider this tetrahedral. Why? Because as we know that tetrahedral field is much more, the difference is, so say this is tetrahedral, this is octahedral. So this difference is much more less compared to octahedral. So delta T is much less compared to sorry, delta octahedral. So that is why we generally compare with the octahedral site, okay, not the tetrahedral, because automatically it will get less in energy. So for the comparison, only consider the octahedral site. And let us give another example for normal spinel. Say cobalt 3O4, same thing, but here your electron configuration is different. So you can write it as cobalt 2, then cobalt 3, sorry, uh, and then O4. So you have to check same thing, CFSE octahedral for cobalt 2 plus. Cobalt 2 plus is 4s0 d7. Second, 3d7. And if you have cobalt 3, you have 4s0 and 3d6. Okay, what will be the electron configuration? Eg, T2g, so 1 2 3 4 5, then 6 7, right? And for cobalt 3, it will be 1 2. Achha, one more thing. So cobalt 3, in presence of any ligand, say nitrogen based or oxygen based, any ligand is there, it will be low spin. Okay, because of the high charge. So as you already have seen that n plus, so depending on n your this value increases. Okay, so it goes to low spin, so it will be low spin. So this is d6, the configuration will be look like this. Okay, now you calculate what will be the CFC value. It will be 6 into minus 0.4, that will be minus 2.4 delta O, and this one will be this is 6 into minus 0.4 plus 2, sorry, this is 5, and then 2 into 0.6. So how much it is coming? Minus 2 plus 1.2, so you have minus 0.8, and here you have minus 2.4. So in terms of negative energy, you can see that cobalt 3 is much more stabilized in octahedral symmetry. So it will mostly go for octahedral sites. So that is why cobalt 2 will stay in the tetrahedral, and cobalt 3 will go for the octahedral, and you have your oxygen lattice. So this will be the structure. Okay. and this will be called as normal spinner. So you can find a lot of another such structures. So how to calculate this one? Just compare the stability in octahedral sites. This is the basic thing. Okay. Now, so let us go to some other topic. Yes. So there are some special part, special cases of transition metal. Transition metal geometry. Okay. So first I will discuss about Young-Taylor distortion. I think already you have come to the topic many times. So this is a very important topic. So when we'll discuss the spectra, color, and other things of compound, so that time, especially, see, important for color and spectra of transition metal complexes. So coordination chemistry is very interesting because of color. Okay, so you can see a lot of color comprising all of the visual, you know, electromagnetic range. Okay, the wavelength and other things. So thing is that, so what you study theoretically and what you observe in experiments, this will be a little bit difficult, like different. So to explain that, you will have to have some knowledge about all these special cases. So where there will be some distortion in the complexes, or it will take the same geometry, or it will, you know, deviate from your ideal or expected geometry. So that things you have to have some idea. So Jahn-Taylor distortion is such cases. Special cases for cases where ideal octahedra is distorted, okay, to lower repulsion energy of electrons by removing the degeneracy. Okay, degeneracy of what? Of orbitals. So this Jahn-Taylor or Jahn-Taylor distortion, whatever you say, so this can be of two types. Jahn-Taylor distortion can be of two types. One is called strong Jahn-Taylor, and one is another called weak Jahn-Taylor. This is with respect to magnitude, or you can say the orbital, okay, absolute orbitals. But apart from the like if you consider the geometrical part, then also you can have two classifications. One can be your Z in, one can be Z out. We will discuss in detail. So, are you following? Are you able to follow up?
Yes, sir.
Okay, thank you. So let us first take this example. Uh, so two scenarios can be there, EG and T2G. So generally Jahn-Teller occurs when there is some asymmetrical electron distribution, okay, in either T2G or EG. So how it will be like, say you have one electron here, okay, so you have degenerate three degenerate orbitals, but you have only one electron in your in one of the orbitals. So where it will stay, which orbital it will stay, okay, like that. So what you have so what consists of T2G? So you have dxz, dyz and dxy, okay. So suppose to lower the energy and to remove the degeneracy, it will stay like this. So you see only one orbital has xy component, okay, z is not there, so it can be like dxy, and 2 will be on the top, dxz, dyz, and then accordingly say dx square minus y square d z square. So this way it can remove the degeneracy, okay. So suppose the electron is staying here. So when there is a when there is a distortion happening with that is associated with the T2G orbitals, that is called weak Jahn-Teller. So generally we can see the weak Jahn-Teller for like say titanium, okay, titanium 2 plus is okay, it will be, I think, okay, titanium you have, I think, D2 configuration, then we will have in T2G like this. So this is an asymmetric electron filling. So in this case you can observe this weak Jahn-Teller, okay, and strong Jahn-Teller always associate with Eg, because Eg is high in energy, and not only that, it interacts with ligand electrons, okay. So because of that repulsion is more. Repulsion is much more in case of Eg set, and that is why we call it strong, okay. So just a second. So by Jahn-Teller you generally lower energy or stabilize the system. So as in weak Jahn-Teller, your associated orbitals will be T2G. So these are in between axis, okay, in between axes. So not directly uh, interacting with ligand, and that is why stabilization less. This is much less pronounced, okay, weak Jahn-Teller, but Eg interacts with ligand more along the axis. So when EG sets are distorted or degeneracy is removed, so stabilization is much more. Stabilization more, and that is why it is strong. Okay, so let me give you some example. So I have already give you one example for weak gentler, that is T2, sorry, titanium 2 plus. Okay, so let us have some example for strong gentler. Mostly strong gentler are are associated with copper 2. Mostly you can see the examples of copper 2 where it is exhibiting a strong gentler. Apart from that, you have also some other uh, compounds, like you have cobalt 2. Okay, cobalt 2, say low spin is your D7 system, and it will be field like 1 2 3 4 5 6 and 7 in EG. Okay, and copper 2 you have like this 1 2 3 4 5 6 7 8 9. So here you have 1 electron excess in EG. Okay, so for copper 2, how it stabilizes? Say so I can name it, let's say dxy dyz dxz. Then you have dx square minus y square, you have dz square. So this can be one option, or what it can be the another way. Let's say in dj square you have 2 electron, dx square minus y square you have 1 electron. This is the another case, and all are filled. Okay, so what does this mean? When you have,
Sir, which
yes,
is Z in, Z out?
yeah, that is what I will come, I will tell.
Sir, okay, sir.
I will tell you. That is why I am discussing this one. So always remember that when there are two electrons in an orbital, their spin will be always anti-parallel. So I am not showing it, but always consider. Okay, when there are two electrons, because when one electron will come to your orbital, so maximum you can keep two. Okay, another one while it will come, it cannot go to the same same spin direction. Okay, it cannot go because there will be so much of repulsion in between them, it cannot stay within one orbital. So that is why they have to rotate their spin direction and stay like this. Okay, this cannot happen, this will be the actual one. And one more thing, so when they are paired, their energy will be less because they will compensate. So suppose you have direction of your spin direction in one particular direction, and other one is cancelling out. Okay, so as a whole your overall energy is less. So energy is less compared to another orbital where you have a single electron. Okay, unpaired electron, so this energy will be much high. So generally what we consider, if you have unpaired electrons, that will be less in energy. Okay, so if that is less in energy, so how it will remove the degeneracy? Suppose this will be dz square, this will be dx square minus y square. So as per this case, okay, as per this case, accordingly, so only z component will be the higher energy, so T2G will also split. So these are the z components, dxz and dyz, both have z, and this will be your dxy. You don't have any z component on this. So electrons will be filled like this way, one and like this. Okay, so wherever you will see that there is a paired electron, that will be lower in energy. Okay, and for this case, what will be the scenario? This will be just opposite. Say this will be your dx square minus y squared, then this will be your dxy, right? This will be dz square and all the z components xz and yz. T electrons will be filled like same. I'm not giving the reaction of spins, you just consider it. Now you compare between these two. Here your dz square is lower in energy. Here dx square y square is lower in energy. Now you check how your both orbitals look like. This is your z. I may draw it with another color. So this is how your orbital look like. This is it. This is x and this is y. Same for another z, x and y. Now let's say this is dz square dx square minus y square. So it will be along the axis x and y, right? And z square will be like a lobe along z and another part. This is your z and this is dx square minus y square. Now in this case, dx square minus y square has low energy. Okay, that means it is not having that much repulsion. So when ligand electron and your metal electrons are repulsing much more, okay, repulsion is much more, then your energy is higher. In this case, dz square energy is higher. Okay, so dz square is repulsing much more with the incoming ligands. So in this case, what will happen? So let's say this is metal, this is your equatorial ligands. Okay, so one thing you can see that equatorial ligands, these are constructed of dx square minus y square. So I can note it down. So dx square minus y square, it is for equatorial and dz square is for axial. Okay, now when dx square minus y square is less in energy, that means these are elongated. These are elongated and axis, z axis is compressed. Okay, ligand are much closer here and ligand are further here. Can you see the relation? Can you see the correlation between this energy difference and the axial equatorial components? Okay, understand, like see it. So when there is less repulsion, x square minus y square, that means they are going far apart, less repulsion. When in z square it is more repulsion, they are coming closer. Okay, that is why it is compressed. So this one is called z in. This is called z in or compressed, and this one is called z out. This one is called z out. All this will come in at the equatorial position. This will be your z out case. So can you understand it, the relation? Okay, so the special, like common shortcut is that you see that where is your paired electron. Okay, the paired electron is in dz square, means dz square is not interacting, so it will be elongated. It will be elongated, that will be z out. Z out means z is elongated. And when you can see that in dz square there is unpaired electron, that is more in energy. More energy means more repulsion, so that is compressed. Okay, is it clear?
Yes, sir. Yes, sir.
Huh, okay. So with that I will give you some practical example. So this question also came in some competitive exams earlier. uh, Say one complex of copper 2 plus So actually this complex is copper NO2 6 4 minus, sorry, NO3 not NO2. So NO3 is a monoanionic ligand, nitrate, monoanionic. Hmm. Then you have suppose this is x minus 6 equal to minus 4, then what will be your x? It will be 2 plus. So copper is 2 plus. And copper 2 plus, what is the configuration? It will be 4s 0 3d 9. Okay, so accordingly you can observe some strong Yanteller effect. Now practically what was done, so you have known about EPS spectra, right? EPS spectra you have known, you know about EPS spectra, anyone? Otherwise I will discuss some brief about the spectroscopy also. Have you heard of EPS spectra, anyone? So EPR stands for electron paramagnetic resonance. Okay, so sometimes people also call it as a ESR. Okay, that is nothing but another term that is called electron spin resonance. You have heard about NMR, right? NMR is very basic thing. Okay, so electron spin resonance is similar to NMR, but there is some differences in how we operate the instrument and how the pulses are generated. So in ESR what happens, you have a electron, free electron. Okay, so it has spin half. Okay, one electron means spin half. Then it can go to two different levels. It can go to two different levels. One is called minus half, one is called plus half. And it can excite, so say minus half is your ground state, and plus half is your excited state. So you can excite your electron from ground to excited state, okay, via external magnetic field. External magnetic field, that is H. So there is a relation, you have a delta E between them. Delta E is G beta H. Okay, you will learn all these things later when you have some spectroscopy courses. So G is a special quantity called G value, or gyromagnetic ratio. Then you have a special constant called beta, and this is your magnetic field, applied magnetic field. And this delta E you can correlate with the wavelength or frequency. So H nu equal to G beta H, and from there we can calculate G value. And G value will give you the location and the environment of electron. So location and environment. And to be EPR active, you must have unpaired electron. So number one is unpaired electron you should have. Unpaired electron. And one more thing is important, that you have a non-zero, non-integer, I think. Not non-integer. Certain nuclear spins. Okay. particular, I don't remember at this point, nuclear spin value, and you should have unpaired electrons. Okay, then what happens actually? So suppose you have your cobalt complex, so this is your copper complex. You have N6 coordination because you have nitrate. Okay, so if there is no janteller, in APR, you can observe only one peak. So APR peak will come like this. Hmm. This is where we vary the field, and this is where we record. So how we'll measure? So suppose you have a energy difference, so we vary the magnetic field. This is magnetic field, and wherever your sample is giving the transition, it will absorb. Say this is like this. It will absorb the radiation, not radiation, and the given wavelength of light. Okay, and then we can have a derivative of this graph, and we can get like this. This is the APR spectra, general APR spectra. Okay, so in this system, in this copper 2 system, you have one unpaired electron. Yeah. If you consider there is no Jantelar effect, then for single unpaired electron the APR peak should come like this. Okay, but we know that copper 2 shows Jantelar. So then what we are why we are getting this kind of uh, isotopic peak? So there is no anisotropy. If there is some Jantelar distortion is happening, your axial and equatorial bond will not be the same, right? So you will not get any isotopic signal, but we are getting one isotopic signal for unpaired electron. So this is actually room temperature data, RT data. When you went to low temperature, suppose say around liquid nitrogen temperature, that is 77 Kelvin or minus 196 degrees Celsius. So that time it changed. That time we could see like this way. So we could see the splitting of peaks, APR peaks. So then researchers suggested that what could be the reason. So then they find out that these bonds, say this is one copper, suppose I am assuming this is Z out case. So there is always a flipping of bonds. Suppose I am assigning them N1, N2, N3, N4, N5 and N6. Always there is some exchange or flipping of bonds. So at any other point you will not get the same nitrogen at that position. Okay, so you will get, say here your N6 has come, here your N2, here is an N4, N5, N1 and what else, N3. So always there will be some jumbling. So at room temperature you cannot freeze, you cannot top or freeze. Okay, but at low temperature this can be freezed. Then you can exactly see the differences, because for your if your axial and equatorial components are not the same, then there will be difference. Okay, there will be splitting of spectra. So this way they could understand that how Jantelar distortion in the complex affects their magnetic property or any physical property. Okay, so This is all about distortion. And one more thing is there, it is uh, other special geometries. Other special geometries, say D8 system. Okay, you have this kind of configuration. Okay, but here in easy set you have dx square minus y square and dz square. Okay, but both of them are not, uh, repelled in similar way, because as I already showed you that dx square minus y square repelled by 4 ligand, right? Because it is along x and y. Okay, suppose this is x, this is y, so 4 ligands will come. This will get much more repulsion. And what about dz square? This will be repelled by how much? 2 ligand, because they are in axial. So say this is z, so only 2 ligands will repel them. So for this reason, sometimes D8 configuration metals like your nickel 2 plus, then all the metals in nickel group, so that is palladium 2 plus, platinum 2 plus, and you can also think of after nickel, so you have copper 3 plus, 2 plus is D9, 3 plus is D8, and after copper you have silver also, then aurum means your gold. So these all can show D8 configuration, and some of them with appropriate ligand field, this can change uh, the geometry from octahedral to square planar. And in square planar you have like this. Sorry, suppose this is your dz square dx square minus y square. So then here you will have d xz dyz. No, this should be the other way. This will be dz square and this will be dx square minus y square. Okay, and this is not delta O for octahedral, this will be delta square planar, is much higher compared to delta O, that is your octahedral one. Okay, so now if you fill it, you have D8, right? So first it will fill this, then this one, 1 2 3 4 5 6, and then this one D8. So generally, sometimes people ask some questions. It comes in netgate something. Say if you have a D8 configuration, say nickel CN4 2 plus like that. So according to your configuration, it should be paramagnetic. Okay. So if you have octahedral coordination, you should have paramagnetic. Okay. Should be paramagnetic, but it actually happens to be diamagnetic. So what is the reason? If you check this one, so in square plane geometry, all the electrons are paired. So that is why it goes to diamagnetic condition. Okay. Suppose you know all the drugs like your platin can be cis, trans, so all are based on platinum. Platinum, ethylene diamine, and then Cl2. This is your structure. So this can be trans, this can be cis, all are square planar structures. Okay, as I told you, all palladium, platinum belonging to the nickel group. Okay, then we started. The very preliminary introduction to molecular magnetism. This is one of my most favorite topics because I am working in magnetism, so my PhD is based on molecular magnetism. So magnetism you can see everywhere. Okay, so starting from our earth to uh, all the things that we use day to day, like your devices, mobile phones, and other any materials you are using. So all these things uses magnetic field. Okay, and there are two components associated with magnetic field, or generally I will say motion. Okay, one is spin, spin along one axis, and another is orbital motion. These are two fundamental things, okay, when you think of any magnetism. And then so what generally happens, suppose you have a free electron, you apply some magnetic field, is a vector, b vector, applied external magnetic field. So then this free electron can align itself, you know so let me represent it another way. Suppose you have some unpaired electrons in the system, randomly oriented. Okay, now you are applying some external magnetic field in particular direction. This is the direction of your external magnetic field. This is a vector. Now what can be happen, these unpaired electrons, these can either align with your magnetic field. hmm? So this will be aligned, or this can be, so when this is aligned, it will be attracted to the magnetic field. Okay, so more we can write like attracted, and when it will align anti-parallel to your magnetic field, this is your magnetic field direction, this is the induced magnetic field direction, okay, this is called H. So this will be repelled, okay. So in this kind of systems we generally call it paramagnetic. When this is repelled we call it dia. Hmm. Then so suppose you have, we have studied in our school and plus 12 that any field say electric field or magnetic field, you can can consider as a line of forces. So this is generally called as flux. Hmm. So suppose you have some magnetic line of forces, these are the directions. So in this direction your B is propagating magnetic field, and this is in vacuum. So I'll give you a pictorial representation of what all the magnetic kind of materials. So this is in vacuum. So all the lines are parallel. You can see it, right? All the lines are parallel. This is in vacuum. There is no disturbance. Now let's say if you are putting a block, some block is there, and this is paramagnetic. This is a paramagnetic box. I'll write it paramagnet. Hmm. Now, what you can predict? What do you think that what will be the effect of this block on the line of forces? So the lines that doesn't come, on the way or the path, or like the lines that are not affected, this will pass straight like this. But the lines that will be close to the box or close to the material, so this will be deviated. It will go like this. See how it is deviating. Suppose the middle one, then you will have this, then you will have this. Can you understand what is happening? The line of forces is going through the material, it is attracting. That is why
Yes,
it is bending, hmm, in vicinity of your material. So this is the case of paramagnetic. Suppose you have diamagnetic case. Just a second. Suppose you have diamagnetic. This is dia. Then this line of forces will not be affected. But which one will be affected? They will go like this. This will be repelled. Hmm. This is the thing. And apart from that, you have another two systems that are called ferro, ferri, and anti-ferromagnetic. So paramagnetic systems are normally the systems when you will apply the magnetic field, they will be attracted to the magnetic field. When you remove that magnetic field external, so their magnetism will be lost. Okay, they cannot preserve their magnetism. That is the property of paramagnet. So these are the ideal cases of magnetic behavior. Diamagnetic is also same. It will not behave different. Okay, after you remove the magnetic field, and then you have some non-linear response where ferromagnetic will do if you remove the external magnetic field, still it will retain intrinsic magnetic field. Okay, this is called ferromagnetic. If you remove it, still it can manage to retain its magnetic field. This is called ferromagnetic substance. And antiferro is so there is a difference between ferro and antiferro. So suppose in your material you have lot of spins differently oriented. Okay, so you apply some magnetic field, and they will be aligned like this. So this is the property of para. And now some of the systems you have domains. Hmm. You have some domains like this is called magnetic domains. So in some domains, inside some domains you have a certain number of unpaired electrons. So suppose you have like this. In each and every domain you have some number of electrons. So when all the domains are aligned along the direction of B, so this can give you ferromagnetic structure, ferromagnetic substance. And then when this can cancel out each other, say exact number of same things, this is one direction, this is another direction, this is another direction. So these are exactly same number of spins that are cancelling each other. So this will give you antiferromagnetic. And in other special case, when you have unequal number of cancellations, so suppose these are at one direction, these are another direction, but this is much more. So resultant magnetic field will remain. Okay, this is called ferrimagnetic. This is called ferrimagnet. So ferromagnetic all will align same. They will retain their magnetic field when we remove our external one. Anti-ferromagnetic, these will cancel out each other. Exact same number of opposite spins. But ferrimagnetic, the number of opposite spins will not be equal. So there is always residual magnetic uh, property. Okay, this is the type of materials. Now, so sometimes these ferromagnetic systems, they sometimes show superconductivity. Acha, one more thing I forgot to discuss. Just a second. So you know how to differentiate uh, all the type of materials. Like you have, suppose this is t-axis temperature and this is your chi. Chi means your Magnetic susceptibility. I will come to this. Magnetic susceptibility means like how much your sample can be magnetized by your external field. Okay, this is called the magnetic susceptibility. I will come to that later. But generally, for paramagnetic, you should expect exponential decreasing curve like this. This is for paramagnetic. This will be ideal case. Sometimes what happens for ferromagnetic cases, so up to a certain temperature limit it will act like a paramagnetic. Okay, all the ferromagnetic act like a paramagnetic up to a certain temperature, then suddenly their magnetism value increases abruptly. Let me show like this. It will be like this. Abruptly it will increase. And at this point, this is called Curie temperature. You heard about Curie temperature? Curie temperature is the temperature sorry, temperature where ferromagnetic material converts to paramagnetic. This is called Curie temperature, huh? CW. Sorry, C only. CW is different. Or TC also people write. So for anti-ferromagnetic, what will be the case? So anti-ferromagnetic also up to some temperature it will behave like a paramagnetic. Okay, and then there will be certain decrease in the susceptibility. So this temperature, where is my cursor? I cannot see. This temperature is called Néel temperature. Tn, and this is temperature where antiferro goes to paramagnetic. Okay, it's clear, right? Okay, let us move to next part. So this ferromagnetic system, sometimes they show what is called superconductivity. So superconductivity is a phenomena. It's very interesting research topic actually, where a material shows zero resistance towards conductance or conductivity conduction of electrons. Okay, so uh, when they show this superconductivity, sometimes they show what is called magnetic levitation effect. So anyone of you know that the most fastest train in the world, what is that? So currently it is in testing phase. It is not being commercially available, but some of the countries have started testing. So what, you know the name of the train that is the fastest in the world? It's very interesting application of this.
AI,
Huh?
AI, AI.
No, no, the fastest train, like the express trains we have, no, the fastest train in the world nowadays.
Okay, okay, sir.
So this is actually called maglev. Okay, you can Google it. So mainly in, Germany and China, they are testing it. Okay, so maglev can reach up to the speed of 1,000 km/h, this much fast. Recently they conducted one testing session also. There it went to 600 kilometers per hour. So this is very, you know, so this was practically achieved 600 kilometer per hour. So this is very, interesting in terms of transportation. So it can travel as fast as a flight, a plane. Okay, so all these are based on magnetic levitation effect. So when you have a superconductors, suppose you have a loop of superconductors, when you have multiple electrons and all are coupled such a way that it behaves as diamagnetic. Okay, it will repel. So what they do in that, in the train, suppose this is your compartment, you have the wheels, here they put electromagnet. Hmm. And in the track is generally, you know uh, some layer of superconductors, and they maintain some of the things like putting some vacuum and other things. So that thing, if you can Google it, you can know much better. So when they apply this magnetic field there, it actually repels. So let's say this is the track, so there will be a repulsion between your track and your, not wheel, actually is the this part, the downside of your deck. So when there will be repulsion, it actually, behave like it is floating on air. Okay, it will behave like floating on air. So you can imagine how fast it can be. If it is floating on air, it is like, just like same way, it can fly. So this is the interesting application of magnetic levitation effect. uh, okay, and let us move into our topic. Yes, so basically in magnetochemistry we are concerned with the spin of electron. Okay, so magnetic property of materials is very important. So we first need to know that why we study the magnetic property. It is very important in terms of, what's some other color? Yes. So magnetic information can help us to, get information on structure, then geometry, okay, and other things also, color and spectra. Hmm. And all this information can help with the application of the metal complex. Okay, so when we are doing the research, what we do, we synthesize our compound or the metal complex, and we generally study the application in different fields, like catalysis, then you can study sensing application, okay, biological biological activity. So there are various applications, okay. So before that we have to have the detailed information of our synthesized compound. So for that, magnetochemistry is very important. So we are generally concerned about magnetochemistry is generally concerned about electrons. And when you are talking about electron spin, mostly electron spin, so one electron can have two spin orientation. One is called up, one is called down. Okay, as simple as that. And along with that, it has an orbital motion. As I previously mentioned, the basic thing of magnetism comes from two things. One is spinning along its own axis, and another is spinning, not spinning, moving in an orbital. So there is two part. One is spin and one is orbital. This is the basic for magnetism. It applies, from miniatures, like from atom to the maximum, like or Earth or universe. Okay, this is the basic thing of magnetism. So from orbital motion, you have orbital angular momentum. From spin, you have spin angular momentum. Okay, can you follow it?
Yes, sir.
Okay. So orbital motion is like that. Say you have a nucleus, I'll put it by n, and your electron is moving in an orbit. Okay. So it has a certain periodicity, mm, or omega, you can write mm, angular frequency, and this is the period, like that. So then your magnetic property, or magnetic moment comes from both spin plus orbital component. Okay, so if you have a metal, suppose this is your metal, and you have your ligands all over it in an octahedral field. hmm? Okay, so you have sorry, you have dn configuration. I'm considering it a general case. So these electrons, if it has unpaired electron, it can spin along its axis, okay, but it cannot, this can be this can be okay, but this cannot move freely. So suppose its orbital motion is arrested. Why? Because this ligand are interacting with the metal. hmm. So all this ligand has some orbital. So I think in this course it is limited. So you have studied about VBT, you have studied about CFT. But as I told you in the last class, anyone like valence bond theory or crystal film theory, all alone is not enough. Okay, all alone is not enough. So that is why we need a combined method, and that actually happened. This is called LFT. LFT is nothing but it is called ligand field theory. In ligand field theory, we combine this CFT, that is your electrostatic interaction, static interaction, and then orbital overlap. Okay, I think LFT is not part of this course. This is pretty much advanced. But you can consider that ligands also has some orbital, metal also has some orbital. So these two orbitals interact. Huh. Due to this interaction, your orbital motion of metal electron, or you can say like orbital angular momentum ceases, right? So what you have, you have mostly spin contribution. Hmm. So this sorry, spin momentum is called by nu s. Nu is moment, magnetic moment. So this is spin only magnetic moment. Nu L is called orbital magnetic. Actually, there is no such term like orbital magnetic moment. This can be called as nu S plus L. Okay, that will be spin plus orbital contribution. Okay, so general theory is that let me write the expression. Right. Okay, this B, as I already told you, I have shown you here. What is B? Just a second. Yes. So this B is the externally applied magnetic field, right? So this B is external magnetic field. H is induced magnetic field. Induced magnetic field means suppose this is your material. This is your material. You are giving, sorry, you are giving external magnetic field, and after that, after that, some magnetic field is induced here. Okay, inside. So that is actually uh, property of your material. Property of your material, induced magnetic field. And then this is called I. I is intensity. Okay, intensity of uh, magnetization. Okay, or the intensity of magnetic field it is being exposed, right? And now you can do one thing. You can divide with h all sides. So b by h will be 1 plus 4 pi I by h, and this I by h, this I by h is actually called kappa. Hmm. Kappa is called volume magnetic susceptibility. So I have already told you once. Just a second. So I have already introduced you to that term. This is called chi. Okay, chi is also magnetic susceptibility. Kappa is also magnetic susceptibility. Okay, so these are actually in terms of units, like how you express it. One is your volume. Okay, one is in terms of your mass. One is in terms of your molarity. Okay, like that, how you present it. So this will be the general term b by h equal to 1 plus 4 pi kappa. This is the preliminary thing, basics. Then this susceptibility, because this intensity depends on the sample, how your sample is uh, exposed to the magnetic field or how it is behaving to the magnetic field. So if you do it in vacuum, kappa is 0. Okay, in that case what happens, b by h equal to 1 or b equal to h. Okay, but in real we don't experiment in vacuum, right? So in practical applications always there is some I value and you will get some kappa or other susceptibility values, and this is a general equation. I will not derive it because it is not required for this course. Hmm? That is for basic magnetism course. If you do it in future, then you can derive it. This is the Curie equation. So this is the ultimate equation. So this is molar susceptibility value. I will write it later. You have n is Avogadro number, nu is your magnetic moment, and then 3 kt. This is not kappa. This is k or kb. Kb, Boltzmann constant. I will write it everything. Just a second. So this is simplified Curie equation. Okay, simplified Curie equation, because you have a lot of other terms, but if you can put the standard values and you can get to this equation, and also from here you can go to this more useful formula, that is nu equal to 2.828 chi mt to the power half. This is the working formula we generally use when we do the magnetic measurement. Okay, and new value you can get it. How you can get new value? Let me discuss that one also. Okay, as I already told you, this mu consists of two parts. One is spin component, we call it S, and then orbital component, orbital component, that is L. And then S is actually number of unpaired. Sorry, I will write it down. I don't have space here. S is actually number of unpaired electron into half, because one electron is always considered as half spin, and orbital component, it can be consist of L1 plus L2. Okay, this also S also can be consist of small s1 plus small s2 plus dot dot dot. This capital L can be considered as small l1 n2 plus l3 plus dot dot dot. Okay, this is for multi-electron systems. And then the combined formula is nu s plus L equal to 4s s plus 1 plus L plus 1 is 1 by half. Okay, and the unit is Bohr magneton. Okay, so generally I told you that here I told you that as your orbital motion is ceased or freezed due to the overlap with ligand, then this L component, L is very less compared to S component, and that is why you can ignore this part. Okay, for 3D metal. Okay, for 3D metals, then what will be your only spin value? This is called spin only. Then will be 4s s plus 1 half, right? And also as S equal to number of unpaired electron into half. So let me represent this one by n. Let me represent this one by n by 2. So let us put this value here, 4 into n by 2, then n by 2 plus 1, right? And if you calculate this, you can get into root over n into n plus 2. This is Bohr magneton. So this formula I think everyone knows. This already we have studied in our class 12. Okay, now uh, okay, so magnetism can give us information about unpaired electrons. Then it can give us information about the spin crossover, high spin to low spin conversions, which itself is a big field. Okay, spin crossover. Then spectra, already said. And what else? Structure. Structural aspects. Okay,
And color.
Spectra is actually related with color. Okay,
Okay. Yes.
accordingly we will get the color. So I'll briefly discuss about these things, spin crossover. So high spin to low spin. So high spin to low spin. Suppose you have this system. If you 2 plus d6. So in low spin and high spin, what will be the difference? This is T2G set. This is EG. This is also EG. This is T2G. In low spin, you have like this, all filled up in T2G. This will be opposite direction. But high spin, it will not be the same. High spin, you will fill one by one and like this. So how do you calculate here? I'll show you the calculations also. So here you see you don't have any unpaired electron. Okay, so our S is 0 here. There is no unpaired electron. S equal to n by 2, right? This is 0. That means S is 0. Now you calculate here. How much will be your spin value? S will be 4 by 2. That is 2, right? Okay. Now you calculate the spin only value. Now you calculate new spin only. So you can calculate by this one, 4s, s plus 1, whatever. This is Bohr magneton. How much it is coming? 4 into 2, then 2 plus 1. So how much? 8 into 3 is root over 24 Bohr magneton. I will not do the exact calculation because this value I can use it in the equation. So what was the equation? Let us get back. This was the equation, right? So new spin only is 2.828. Okay, then chi m molar chi t into half. Now let us square it. New SO square will be 2.208. That square will be roughly around 8. Then you have chi m t. You know your spin only magnetic moment, that is root over 24. The square will be 24. Then you have 8 chi mt. So what will be your chi mt value? Will be 24 by 8, that is 3. So why I am representing this chi mt value? This is called chi mt is called temperature product. This is multiplication product of molar susceptibility. Okay, so this is the term this is the term used in research. Whenever you will see any paper or article concerning any magnetic property of any molecule, you will see this term that is called chi mt. Generally we use this term. So that is how we calculate. So for Fe, how much it was? 2 plus high spin chi mt value calculated was 3. Okay, and this unit is a little bit different. This will be centimeter cube, mole inverse Kelvin. So that details I will not go how the unit comes because we need to go through the derivations. And for low spin, for Fe2 low spin chi mt calculated will be 0, right? Because see here, your s is 0, everything is 0, your this moment will be 0, and chi-mt also will be 0. So 0 centimeter cube mole inverse Kelvin. Generally what happens, what experimental data we got, just a second. This is the kind of experimental data we got. Here I am plotting chi-mt. This is my temperature axis. Say this is 0 starting point, and we will get like this. This is a typical spin crossover curve, and this value will be somewhere 3. Okay, I am showing it for 1 Fe2 center. Okay, so you can see it is not exactly close to the 3. So when we do any measurement on some iron 2 complexes, we don't get what we theoretically calculate or expect for an iron 2 high spin. We generally get some excess susceptibility product. Hmm. And here comes that small orbital contribution. So as I told you, think in some earlier slides. Yes. So here what I told you, orbital angular momentum ceases or quenches, but not fully it will vanish. There will be small part. Okay. So sometimes for some metal ions, like just a second, for some metal ions, mostly for cobalt to high spin D7 system, then iron 2 high spin also. Okay, you can see more than expected magnetic moment. So this is due to small amount of orbital contribution. Okay, or in other terms we call it spin orbit coupling. Can you understand?
Yes,
So
sir. Yes, sir.
sometimes in exams this type of question comes. They will give they will let you know the metal center which is present, and they will ask that expected magnetic moment doesn't match with the uh, like experimental value, so it is little more than expected. So what is the reason? So for 3D metals like this cobalt 2 or iron 2, okay, so generally we observe generally observed for more than half field cases. Okay, more than half field cases. Okay, more than D5 configuration. So there we see it, this spin orbit coupling. Sorry. Okay, that's fine. Yes, one more thing is there. So this spin crossover, chi-mt, acha, chi-mt, chi-m is your molar susceptibility. Then you have chi g, that is called gram susceptibility. Ability. And you have volume susceptibility, that is called kappa, that you already know. So volume susceptibility. So you can interchange all three. How can you interchange? So you can divide by density, you can play with them. So it will be like chi m will be chi g into molecular weight, right? Just the way we calculate the molarity. Then chi g will be kappa by density. huh? Volume by density will get the mass, same thing. hmm. And what else? Okay, so this chi-mt curve, this is the normal one that I showed you. This is called gradual. uh, Gradual when suppose you have metal centers. So in your complex, what you have? Some of the times you have monometallic complexes. Monometallic means you have this coordination, 6n, n6 coordination. This is called monometallic. Sometimes you have bimetallic complexes. You have all ligands. You have all ligands. Then you can have trimetallic also. Okay, you can have some polymeric complexes. Huh.
Monodentate, bidentate.
No, not monodentate bidentate. Monodentate bidentate in terms of ligand. Okay, so suppose you have this one. This is called bidentate. Bidentate is the ligand. In comparison to this one, only pyridine if you consider, this will be monodentate. But this is ligand. This is monometallic, this is bimetallic, trimetallic and polymetallic. Okay, monometallic, bimetallic, tri, and then polymeric complexes. So what I want you to understand is that when there is more than one metal center present in the system, okay, so there is some communication between them. There is some communication between them. If the communication is weak, then your curve will show like this, gradual. If the communication is strong, then what will happen? You will see this kind of curve. You will see this kind of curve. Sorry, not this. Okay, this is called abrupt. Abrupt means, say one metal center is going through a change, then it will communicate with the other metal center. It will also going through a change. It will go through a change. This will communicate with the other one. It will also go through a change. So all this will be a series. Like a domino. Okay, you start uh, putting one sequence or something, so eventually all will go hmm, in a short space of time. This is called abrupt transition. So in spin crossover, gradual transition happens within a temperature range of 100 Kelvin, 100 degrees Celsius, whatever, within a temperature range. And this abrupt transition happens within a range of 10 degrees C or Kelvin. You can see this range, if you talk about, this is very narrow, this is broad. Okay, and sometimes also what happen, if you go from low to high temperature, it will follow a separate path, but when you are coming down the same system, when you are coming, it will not follow the same path. Okay, just a second. When you are coming down, it will follow a different path. So this thing is called, this part of plot is called a hysteresis. And this is called hysteresis. temperature with this hysteresis is associated with strongly correlated system. So this communication that I told you, within metal centers, these are called cooperativity or strong communication. So when there is so strong communication, once your system changes the property, when it is going back or going down again to the low temperature, this will not follow the same temperature. Okay, so this will be non-linear behavior, something kind of. Okay, and I think I have saw something like pressure effect on electron configuration. I think in some of the lectures one question or something was discussed. So I'll just give you a brief example or spin crossover. So this is a huge, very interesting topic, pressure effect. So generally, uh, you have this gap, delta O between EG and T2G. So for easy system, I don't do. I will give you example. This is low spin system. When it is low spin, because delta 0 is greater than pairing energy. Pairing energy is less. That is why it is pairing. And this happens for which kind of ligand? Strong field ligand. Strong field. Strong field ligand. Then you have another case where you have EG, T2G, D5 and D6. So in this case, it will be high spin. Why this is high spin? Because delta 0 is lower than P. This energy is lower, so it can jump. It can easily jump from T2G to EG, so it will not pair. So for which case we generally observe it? For weak field ligand. Strong field ligand is CN, CO, like that. Weak field will be any halide, OH, then H2O, like that. Now what you can do, this is the actually I work in this field, so you can tune this delta 0. How you can tune? You can design certain ligand. Okay, design certain ligand that will give you an optimum field, so that this delta 0 is a energy, right? Is a energy. This will come in the range of kBt. kBt is what? This is thermal energy. hmm? This is thermal energy. So in this case, delta 0 is much small for weak field. For strong field, delta 0 is much higher. But for a certain optimum field, you can tune this delta 0 so that you can interplay. So this kBt or delta 0, so this small energy, this energy will be so small, we can supply externally. This energy we can supply externally. So what we do, we generally excite this molecule with what is called external stimuli. External stimuli may be physical, temperature, pressure, light, then electric field, magnetic field, or chemical. These are all physical. Chemical can be your chemical potential, nu, pH. These are all chemical stimuli. Then you can give this energy, and it can convert between high spin, low spin. This is a very exciting research field.
Sir, how many unpaired electrons in this?
Here, no, it will be intermediate. So, you know, you can vary this delta 0. If your delta 0 is high, then it will be this configuration. If your delta 0 is low, this will be this configuration. So this curve I show now. So this is 0 state. At this position, say at this position, it is all at low spin state. Low spin state is this one. This is your low spin state. And at this position, all are in high spin state. This is your high spin. So say what we are varying here, temperature. That is what I have written, temperature. We are giving this external energy, temperature, so that it is converting to low spin to high spin. And you know what is the very interesting thing here? So you will have different, why that color goes away? You will have different color of these two state. Okay, this one will be yellow, high spin, and this one will be dark pink. You can gradually see it. So when you will change the temperature, you can see the change in the color and the spectroscopy. Everything will change. If you do UVB spectroscopy, then IR spectroscopy, everything will change. This is a very interesting thing. Just by using temperature, pressure, or light. So I'll show you once again. Let's say this is your temperature and you have this magnetic information. This is your normal temperature curve. Okay, this is your high spin state, this is your low spin state. Same thing you can go by light also. So this is for temperature. If you shine light at this low temperature, it will come to this state. Okay, and it will stay like this. So this will be your H nu, temperature fixed at low temperature. So see, we can vary by temperature input also, by light also. One more interesting thing is that you can use pressure. Okay, pressure is also a good thing. So how pressure is introduced? If you vary pressure, so if you introduce pressure, it will be like this. So generally pressure application. So when it is changing its state, na, so one certain value is called the middle point of your transition. It is called T half. T half means transition temperature. Transition temperature. So if you apply pressure, your T half shifts to higher temperature. So there is a relation between pressure and all this study. So what is happening? Let's say we can understand it from here. So in low spin state, we are all having in T2G. The electrons are in T2G, but in high spin state it is going to EG. So you remember our barycenter was in here somewhere, the zero level. These are stabilized, these are destabilized, right? So when you are putting your electrons in the anti-bonding level, this is anti-bonding, then what will happen? It will destabilize. It will destabilize the system. And so if you have some iron nitrogen bond distances, so you have all nitrogen, like 1 2 3 4 5 6. My geometry is not good, so just consider this iron nitrogen bond distance. So At low spin it will be less bond distance. Bond distance compared to, do it proper way, in the high spin state. You understand, because in this case electrons are going into the Eg level, that is anti-bonding. That is why this, you know, bond distance is getting increased, energy is higher. So when you are putting the pressure, suppose it is in already in high spin state, you are putting pressure. So this is your molecule, you are putting pressure. Okay. Now what will happen? These bonds, will be shrinked. Okay. Upon application of pressure, upon application of pressure, all these bonds will shrink. So that is why it will stabilize low spin state. That is what you can see it. Say suppose one temperature, I take this temperature, say this temperature. Now you see at this temperature, at normal light irradiation or in temperature variation, you can see the stability of high spin. But when you are introducing pressure into the system, it is going to the low spin state. Okay. So pressure always stabilizes low spin state, because it will put a, you know, uh, it will compress the bonds, at all direction. And that is why your T half temperature, this is T half temperature, shifts to higher temperature. This is higher temperature. Is it clear? This is very interesting thing.
Yes, sir. Yes, sir.
Hmm. So nowadays people, study this temperature, electric field, magnetic field. So earlier spin crossover field was only uh, explored by temperature variation. Nowadays people are using some other things. So one thing is pressure out of this pressure variation. Okay, this is fine. One more thing is there. So this is the last topic. Then I will discuss 2-3 questions and then we'll wrap up for today. So I already showed you. Just a second. Chi value is n moment square mu square by 3 kt. So for a certain system, particular system, this value, this value and this value will be constant. Then we can write as x equal to 1 by t, or chi equal to chi proportional to 1 by t, or chi equal to c by t. So this we can call c equal to this n mu 0 square by 3 kb. This is Boltzmann's constant. So this is called Curie constant, and this is called Curie equation. But this situation is ideal. Situation is ideal. Normally, practically, there is a temperature correction term. So that is called C by T minus theta. Hmm. This is a temperature correction, and this is the correction of Curie law. It is known as Curie-Weiss law. Just remember it. There is a correction of Curie-Weiss law for for practical systems. Okay. So with that, I move to some questions now. The 4 questions we'll discuss today. So you already discussed about CFAC and other things. Okay, so this is the question. So it says that among the following complexes, which one shows zero crystal field stabilization energy? So what are the metal ions? One is manganese 3, iron 3, cobalt 2, and cobalt 3. So what can you say? What will be the answer? Any idea? See, manganese 3 is a D4 system. Iron 3 will be D5, 5, cobalt 2 will be D7.
B answer.
Huh?
B.
B. Okay, because water H2O is always weak ligand. So if there is chance of any high spin, low spin species, it will always from high spin. So if you consider all the scenario, for D4 it will be 1, 2, 3, 4. Iron it will be 1, 2, 3, 4, 5. Cobalt 2 D7 will be 1, 2, 3, 4, 5, 6, 7. And cobalt 3 D6, same like iron 2. Sorry, cobalt 3 will be low spin always. Yeah, cobalt 3 will be low spin. Huh? So you can see that if you calculate for this one, 2 into 0.6 plus minus 0.4 into 3. So 1.2 minus 1.2, it will be 0. Okay, this will be the
Yes, sir.
right. This will be the
Yes.
right answer. Now go to the next question. Magnetic moment of an octahedral cobalt complex is 4. Electronic configuration of the complex. So you have to back calculate it. Can you try? So this is your, I think, new spin only value. You can use either of this one or n plus 2. Anyone you can use. Now you calculate the number of unpaired electrons and tell me. Which one will be the answer?
D answer.
Sorry,
D. D.
D. How? Let us calculate this one. So n plus 2 will be 4. Then will be 16 n square plus 2n minus 16 is 0. So number of what is the number of n you got? So let me calculate like this way. 16. It is matching or not? Just a second. So let me back calculate. So cobalt 2 will have D7. So for high spin, it will have, so 3 is 2 is 15. So it should have 3.9 actually. So this has given wrong. Hmm.
Yes, sir. Yes, sir. Yes, sir.
It should come 3.9. So if it has D7, then it will have this configuration, right? T2G5 and Eg2, right?
Yes, sir.
So A will be the right answer. So cobalt 2, as it is D7, you can have either high spin or low spin. Okay. But here they have given 4.0. So if you have cobalt 2 low spin, then you should had like this configuration 1, 2, 3, 4, 5, 6, and 7. So you would have 1 only. Hmm? For 1, you had n into n plus 2. That means uh, root over 3, and that will be 1.73. So from the moment also you can check it. Okay, so this is the moment for high spin complex. So high spin you have D7, so this will be the configuration. Low spin it would have been much lower, the magnetic moment. Okay, clear? Okay, let me move to the next question. So spinel structure is shown by, and there are some chemical formula given. So I have shown you that general formula for spinel,
D is right.
yes, Ab2O4. Okay, so Ab can be same ion or different, doesn't matter. So you can see here everyone has 3 metal ions. Okay, so these are actually Ab2O4. So all of this will be the spinel structure. So this is the last question. Which of the following is paramagnetic? Can you tell me? So this is the tetrahedral complex, cobalt Br4 2 minus, cobalt is in plus 2, molybdenum is in 0 state here, uh, platinum is in 2 state, and cobalt is in 3 state.
A is the answer. A.
Yes, A will be the answer. So cobalt 3, as I told you, it will be always low spin with oxygen or nitrogen donor. Hmm. Donor ligand. Platinum 2, I have shown you one example. It will come with same nickel group, nickel 2 group, where it will show square planar geometry. Hmm. So this is a D8 system. Square planar will be like this. 1, 2,
Diamond.
3, 4, 5, 6, 7, 8. So all are paired. There is no unpaired electron. So this will be
Diamond.
diamagnetic. Molybdenum 0. So molybdenum comes with chromium group. Chromium, molybdenum, tungsten. Okay. So molybdenum generally it has I think 4s, not 4s, 5s. Just a second. Chromium, molybdenum, tungsten, yes. For 5s2 for D4. Hmm. But when there is carbon associated, this electron configuration will change. So this will be like
Yes.
40,
45 U.
not 45, 46. Okay, so that it will be, all paired. So there will be no unpaired electronegative system because of the carbonyl groups. Carbonyl are most high field ligand.
Yes.
So you see the spectrochemical series. Chemical series. Carbonyl is in the extreme right.
Yes, sir.
Extreme right. So this is so powerful ligand field it generates, so that it will go to complete low spin state, diamagnetic. Only for cobalt Br2 you have this tetrahedral, and as it is high spin, so 1 2 3 4 5 6 7, so you have 3 unpaired electron. So this will be your paramagnetic species. Okay, so with that we finish today's talk, or the discussion, and I'll meet you in the next class. And when is your exam for this course?
22 March.
March 22nd.
March
March
22nd.
22.
So uh, we'll have one general class left for this course, but if you have some particular doubts, so then you can ask. Okay, so you can take one more class, like special classes for doubt. You study all this materials and whatever you have got. If you have any doubts, you just let me or the other TA you have, so that we can conduct extra class for just doubt clearing. Okay, for your exam.
Sir, can we get the recorded classes of these interactive sessions?
Just ask a question.
A recorded class you are getting, no? Because we are uploading that recorded classes.
Yes, sir. Yes, sir. Yes, sir.
Just ask a
See,
question.
you are
Sir,
getting.
is there any specific study material for basic inorganic chemistry? PDF form?
I think in this course page, so there you can get some name of the books, right? There is some. Let me just go into it. And
Actually, here provide a books regarding basic inorganic chemistry, but when we reading this book is not sufficient for solving question answer or assignment.
which book is referred?
Which book one specific books here refer basic inorganic chemistry provided by Professor. Just a minute, sir. See this,
I
but
am also checking. I have not checked this one. I am also checking.
actually this book is not enough for solving assignment and other related question answer.
Let me just check one minute. I am checking this one. Okay, okay,
Actually,
okay.
basic inorganic chemistry, Professor D. Maitri, chemistry
Uh-huh.
IIT.
Yeah, this
Actually,
one,
this
no.
book is just introducing about basic idea in basic inorganic
No, no,
chemistry.
no, no. This is not a book. This is whatever sir has taught in each lectures.
Hmm.
Okay, this is just a description of all the slides. This is not a book.
Actually, please
Uh,
provide some
mm,
specific study material uh, throughout this course. That is 1 month, 1 month courses. Um,
okay, I can
I
suggest you some preliminary books. So this coordination chemistry will find in Huhi. So you know about Huhi book.
I have lots
Yes, sir.
of books.
Yes.
Okay, yes.
So this coordination chemistry you can find from Huhi, and some more books are there. Just let me check.
Just one question. How I preparing for online exam, which will be called after submission my assignment when exam will be happened. How I prepare? How will I prepare?
Yeah, so how the exam will be conducted, we still have to check with the orientation team how they are conducting, because we may have to help them. So that thing we are checking. Okay, we don't also we don't have the clear idea about how it will be conducted. So that in time you will get to know. But just a second, I will give you some books.
All YouTube lectures provide already discussed by sir, and
Uh,
all assignments and any additional matter if here.
Did you guys have that book RP Sarkar?
Yes, yes, yes,
Huh?
yes,
So RP Sarkar second part, the second volume.
yes.
This is very useful for this course. Okay. Actually, we also have the same course in our institute. So that time when I was TA for this course, I actually suggested this one to every student. Okay. So this will help you a lot. And for general chemistry, any book you can read. For coordination, I am suggesting RP Sarkar and Huhi, because for spectroscopy and color, like that part, spectra, Huhi is best. Okay, all these diagrams like your Orgel, Tanabe Sugano, I think that is in the last week, all the lectures. So that book is best. If you can study these two chapters, na, so your basic will be much more improved. So whenever in future, if you try to like apply all these things, so your basic will be very good with these two books. So I will suggest go for these two books. One is Huhi and this RP Sarkar second volume. Huh?
Mhm.
And I have some other books also. I will just check it and I will let you know in the next class. For the moment, you can suggest. I can suggest you these two books. This will be best applicable for this course.
Okay, okay.
And I think some bioinorganic part will be there in the last week. So for that part, you can study some materials, because bioinorganic is very vast field. Huh? So if you want to study some books for that, it will take much more time.
Which specific material for bioinorganic chemistry?
I will check it. I will check, and if needed, I can supply to you also. Not a problem. I will check and let you know. Next class, I will let you know.
Okay, sir, just I request before exam 22 March, you can brief total idea about the whole courses. This is my request.
Okay, that we can do. But what I actually suggest you is that you go
Mm.
through the course, and whenever you are having any doubt in some parts, no, you let me or the other TA know, so that we can specifically conduct some session for that part.
Okay,
Okay.
sir.
We can discuss some questions like your competitive exam questions, and like what will be the type of questions that will appear in the exam.
Okay, sir. Thank you.
That will be better. You just go through the parts, all of the parts. Whenever you have any doubts or difficulty for understanding that things, you can let us know. Okay, so thank you all. We'll meet in the
Thank you
next
so
class.
much. Thank you so much.
Thank you. Thank you.
Thank you, sir.
Thank you.
Bye.